start recording. Yeah, that looks right. All right, I think I'm in. Can you guys hear me okay? Okay, cool. Make sure I share my screen. So a couple of bookkeeping type things. This is week 4 of 5. Next week is week 5 of 5. Next week is the last week then. I'm asking the powers that be when the final grades are due so that I can give you as much time as possible before the last possible second the grades are due to do next week's stuff, which will probably be one last assignment in lab and also the take-home final. So there's a non-zero chance that the day all that stuff is due is going to be next Friday. So you might have a busy week in the middle of the week next week trying to get a bunch of stuff done. If that's the case, I'll make the homework part of the stuff next week be less big so that you can concentrate on the final. But it is coming. So things you have left to worry about are, I guess I can write this down. Things you have left to worry about. What's left? First is the web page, due today. Second is homework 4, assigned today, which I'll talk about today. I'll also talk about the web page stuff too if you guys have any questions once I get through this list. Then homework 5, which will be on stuff we're doing the end of this week and next week. And then the last thing is the final, which is going to be take home. It's going to look pretty similar to the homeworks in the sense that it'll be a lot of short little questions for you to answer. It might talk more about the ideas instead of the details of how to use some of these programs, but that's in terms of format, it'll probably look pretty similar to the homeworks. Yeah. So once I know the latest I can hand in the final grades, that minus a day or half a day will be when everything's due in the last week, so that you have as much time as I'm allowed to give you to work on this stuff. So that's my plan. So hopefully we can get this figured out and done. Hopefully it won't be too crazy and too much stuff. I don't think so. I think this week is. I think this week is fun stuff. I guess we'll see if you think it's fun stuff. And then next week is the last week. All right. So the first thing on this list is the web page. So I was going to ask you. I know a lot of you guys have been emailing me and asking me for help about how to get their web page and stuff working. If you have any questions you want to ask me now about problems you're having or questions you have about what's going on or whatever. 20 seconds. All right. Whoa, a lot of questions. All right. First, I'm not sure the picture thing ever worked. Well, all right. So your thing, the picture thing. So you're, Sarah, you talking about the thing we just did 5 minutes ago? Okay. So let me load. I'm going to show everybody your webpage here. I don't know what you moved stuff around to, so it's going to look a little. I'll have to check. So Sarah was saying that she had trouble loading the image on her page. Remind me what your email ID is. SCSANS4. All right. So let me drag this over and share your page. Try to share your page. All right. So this pink page is your page. If I go to view page source, to remember this here, this thing that's ingress.html in your page, that needs to be changed to the name. Well, that's what I got. So I mean, again, I don't know where your what's been changed because of your. So what you did was you had this stuff in this file folder. I don't know if this is going to work or not. So yes, that's gone now. So what I'm seeing with the page that I'm looking at right now is the index.html page in your public HTML folder. If that's not the page I'm supposed to be looking at, if you change something and put it someplace else, then I don't know where what you've been moving around and what you've been changing. So if you have multiple copies of your stuff floating around, because you have this stuff and you have another folder with other stuff, you got to make sure that when you change it, you're changing the right place and that you're looking in the place you actually changed as opposed to someplace else. So all I can tell you is, yeah, the page that I'm loading has this image link, which is not the right image link. So, yeah. As far as what exactly you meant to do, I don't know. I couldn't tell you off the top of my head. All right, cool. All right, next, Richie says, you remember if I told you to connect the service in order to disconnect you to 20 seconds of inactivity? 20 seconds seems kind of low. I wonder if... So this is my FileZilla program. I'm wondering if there's a preference in here. Yeah, aha! So here's what I did. I went to FileZilla. I went to Settings. I don't know if you can see this window that pops up, but apparently you can't see this window that pops up. So let me share the window that popped up. So if I go to FileZilla and then Settings, what pops up is this window here. Okay. And what happens in here is, you see over here it says timeout in seconds. And so what you can change is that to be whatever number you want, and then say OK, and then it ought to time out after longer. So that's how I would fix that if the 20 seconds annoys you. Does that make sense? All right. Third, we have an example of how much content we need for our webpage. Not really. I would, because the last time I taught this class was a long time ago and those people graduated. Let me see if I can spy on somebody who took this class, a long time ago, and I have to look them up, so give me a second. So let me see who got a good grade in this class the last time I taught it. This is homework. This was homework 6. Samantha Simon, do you still exist? No. Yeah, I think all of these pages are have been taken down by the web server, unfortunately. So all the stuff from the last time I taught this class. Yeah. So what I would so certainly if you want to show it to me and say, hey, is this enough? I'll tell you. I would say what I want is a couple or a few paragraphs per page with links and pictures and stuff. That's about the size I'm going for. So if you just have, 2 sentences, that's not enough. If you can certainly go on for pages and pages and pages if you want, but you don't need to. A couple of paragraphs, a couple of pictures, a couple of links, a couple of cool stuff. That's what I'm looking for. Something that looks like it's a legitimate enough page that people would want to go there and get some actual information, even if the information is not very exciting. So I guess that's what I would say. So that's my unsatisfying response, I guess. All right. Any other questions about the web page? How it's working? Most everybody seems to have been able to transfer the files over at least and get the permissions working and stuff like that. So that's good. I guess a couple people have trouble with the images. One of the problems. Let's look at your page. You are. Is it on the server? So, remind me of your ID. HJ Baker. Why did that not work? Oh, because you're calling it. All right. So let's share this page. So let me make sure I'm doing the right page here. I'm looking at, second HTML. Okay, so this is your page. This is the link to the football. So this is the link to woo. All right, so you can. I don't know if you can see it, but on the very bottom of my screen of the window, it pops up what the link is, and the link says something like go.ou.edu/twiddleu/ a bunch of weird symbols /%u/http. So what it's trying to do is it's trying to find a file named http://creefrombrowns.com on your server. So let's look at your source and see why that's. I think it's because of these weird question marks around your link. And what those weird question marks tend to be is if you're not doing it in a text editor, if you're not editing your file in a text editor, if you're editing it in a word processor and trying to save it, or if you're trying to copy and paste the link information from the Word document I sent you, then what they give you for quotes by default are these angly quotes that look like that, with the angles on them. What you really need is the straight block quotes. And if you do one instead of the other, then if it's not the block quotes, so do they look like straight quotes? Because they're not on them. They're not on here, is what I'm saying. Well, then I don't tell you. All right. All right. Can you open the editor now? Let's all look at your screen. Or are you on a different machine that doesn't have it? All right. Open it up and then share your screen, and we'll all take a look at it. I think I might have to let you look at it. All right, can you guys all see his editing? Yeah, those are angle quotes. You can tell because they're angled. See how they look kind of curvy? So you try to go in and erase it and replace it with a straight regular quote. Yes. That's what it is. I bet you that'll fix the problem. Okay, cool. Yep. All right. So it looks like most of you, everybody I've talked to, is on the way towards getting it working. I guess people I haven't heard from, so hopefully you guys aren't totally stuck. So Cool. Any other questions or problems or anything with this stuff? Going once. Going twice. All right, cool. So yeah, I'll be around today. If you get stuck again, let me know. Send me an email. I'll do what I can. It'll be hard to give you a lot of help, with only a few hours left before it's due, but we'll do what we can. All right, today, this week is about programs and programming languages. So way back in the beginning, I said computer science is the study of algorithms. An algorithm is a step-by-step solution to a problem. And a program is an algorithm where the steps of the algorithm are written in a language that a computer can understand. So I told you this at the beginning to make you understand the difference between algorithms and programs, and then I told you it, I think, in the second week to show you what machine language is and that was that horrible homework too with the B machine and the zeros and the fives and the nines and the negating and all that stuff, which I sent back to you. And if you care, my answers to that are on the blackboard, so you can look at it. But the point of the machine language was each instruction in machine language gets implemented as electronic circuits. And this is beyond what we have to do in this class, but just know that it's possible to make electronic circuits that take in a bunch of electronic signals that have zeros and ones on them, where 0 is off and 1 is on, so there's either power on the wire or there's not. And another set of signals, again, on wires where 0 is off and 1 is on, do a bunch of electronic nonsense to it with transistors and gates and things like that, and then spit out the sum, which we can interpret as a binary number that has zeros and ones equal to the sum of the binary numbers, the things that came in. How that works is not important. It's worth knowing that's what a computer actually does, is it has circuits that do things to wires, and the fact that we're interpreting those wires as bits and those bits as numbers or whatever is how a computer works. The point I want to make today is that almost all real programming is not done in machine language. So I wasn't showing you the machine language because I was showing you how real programmers do real programming and how real programs look. I was showing it to you to show you what a computer really does under the hood and get you a feel for the fetch execute cycle, get you a feel for the idea that memory and instructions live at addresses in memory, and then data gets copied into registers and all that kind of stuff. Okay. Instead, well, let me go back a second. Most programming is not done in machine language because it's very tedious and hard to understand. Tedious because you saw what you had to go through just to subtract even two numbers, right? You had to take a number, you had to load an F into the thing, you had to call the instruction 9, you had to load a 1, you had to add 1, and that negated the thing, and then you had to add it to the original thing to subtract it. And that was a lot of work just to, if all you want to do is A minus B, it took you like 7 instructions to do it. And so imagine what multiply is like. It's not fun. It's adding over and over and over again in the loop. Imagine what divide is. It's even worse because you have to guess and see if it goes into it and then back it up if it doesn't and things like that. And that's just basic arithmetic. Real programs do lots of complicated stuff, and having to do everything at such a very, very small granularity at a very, very machine-specific level where everything is spelled out exactly in terms of circuits is way too hard and way too long and not what we want to do. Okay, so instead, people have developed what are called high-level languages. These languages look more like English in the sense that they're not just combinations of numbers. And programs in these languages get translated into machine language before being run. So the idea is I wasn't lying when I said the machine has to use machine language to do anything, okay? But the difference between the machine having to use machine language to do anything and the fact that most people do programming in a high-level language is that there's this translation that goes on that turns your high-level language program into the machine language so that the computer can understand it. And so the benefit is when you program, you can program in something that looks kind of close to English, and then when it runs, it'll run in the machine language the computer understands. And so if you've ever seen somebody programming in the movies, you'll see them with I'm going to try to share this image I found online here, see if this works. You'll see a screen that looks kind of like this, with a lot of weird words and stuff, and it kind of lines up, and there's like things with lines and semicolons. Anybody who programs in a movie or a TV show is going to spit out a bunch of stuff that looks like this, and you kind of have a feeling for what this looks like. This is a high-level language. I don't know what this program does, but it's part of a high-level language program. And what the point I want you to make is you can at least notice words in here that look close to English, right? There's a word color, there's a word red and green and blue, and there's, average and sizes and stuff like that in there. And the commands are not zeros and ones. They're not hexadecimal numbers even. They're not anything like that. They're just things that it looks still wacky, but it looks at least semi-close to English. Okay? So the job of so there's lots of different programming languages out there. So lots of different high-level languages. Boy, that is a badly written word. Exist. Some of you might have heard of the one we use here in most of our classes. It's called C++. There's also a language called Java, and so all of those Java programs that I made you load all semester and set the security stuff of are programs written in this programming language called Java. Some places use a language called Python, because it goes on lots and lots of different languages. And so what I'm not going to do is teach you how to use these languages because, for example, C++, our entire CS110 course is basically teaching you the basics of how C++ works. So there's no way I'm going to get you to learn that in a week. But what I want to talk about is how they all have common features. And what those common features are ways to give combinations of machine instructions as what's called an abstraction. An abstraction is something that looks like a single piece, but really is more complicated when you look closer. And we do abstractions all the time. When somebody, I'm thinking about the election. So when somebody takes a poll of the electorate and says the people at large want Donald Trump or whoever to win the election, what they're saying is an abstraction of lots of individual people with lots of individual opinions that all get glommed together into one abstraction of all the voters. When I look at a chair, I think of it as one unit, but it's really abstracted into the back and the handles and the legs and all that stuff. Okay, so computer science has a lot of abstractions in it as well, but they're not concrete things. They're more abstract abstractions. How about that? So, for example, so things like instructions to repeat parts of the program over. And so high-level languages have relatively simple ways to wrap a bunch of your program up and say, do this over and over again. And that was the kind of stuff you were doing in the machine language homework with that add the numbers from 1 to 10 or 1 to 15 or 3 to 12 or whatever program that I was trying to make you do a couple times. It let you do an addition over and over and had jumps back and forth to do it over again, and it was hard to keep track of what was jumping where and when and why, right? And so what a high-level language will do is will give you an abstraction that'll hopefully make it easier to at least see what's being jumped around. Instructions to do certain things sometimes. So when you did the addition checker, which was the last question on the homework, you had to load two numbers up and add them, and if they were the sum that you got from adding them was the same as the sum you loaded from memory, then you put a 1 out, otherwise you put a 0 out. So you did certain instructions sometimes, but it was hard to figure out what was going on. There was certainly no part of your program that was obviously, just by looking at it, the stuff I did if they were equal versus the stuff I did if they were not equal. You had to just know by looking pretty closely at the program what instructions were happening all the time and what instructions were happening sometimes and what instructions were happening the other times. And so a high-level language will better give you an idea of what's happening when and what's happening sometimes. The other big one is doing some abstractions of memory. If you remember the machine language stuff, we just said memory is a collection of data at locations, and we can load something from position 40, from memory address 40, or we can store something into memory address 42 or whatever. But there was no way of knowing why we cared about location 40. So what we can do now is give locations names. These locations are called variables. And what a variable is to us is a location in memory. It has a name. So a lot of those things you saw in that picture were variables. The location, the data at that location has a value. So I'm telling you this because I want you to kind of get an idea of the kinds of stuff you can do in a high-level language and how it's going to be a lot easier to program stuff in a high-level language than it is in machine language. Okay, so machine language was about understanding how the computer worked. High-level language is going to be more about how programs work, kind of. The language we're going to use is called Scratch. Scratch is it's located at scratch.mit.edu. So really smart people at MIT have invented this language. It's designed to let people with no programming background i.e. people like you, it's designed for people with no programming background to quickly do some cool graphical stuff. So it's not great at math. It's not great at data entry kind of stuff. What it's good at is letting you do some cool graphical stuff, making your own easy video game kind of stuff relatively simply. So what I want to do for a little bit of time now is just show you what it looks like so that you can see what happens. So let me go here and let me share the screen. Come back here. The green arrow keeps hiding from me. So when you go to scratch.mit.edu, this page comes up. What you want to do is click the Join Scratch button on the top to create an account. So the whole language exists online. There's nothing to download or install. I already have an account. And so I can log in and what you should be able to get is, so now what you want to do is hit create your own. Create your own says I'm going to make my own program. Okay. And the lab is going to walk you through exactly how this works in terms of what instructions there are and working you towards making the homework works. And now I'm wondering what this is going to load. Okay. And so you get this advertisement with Cartoon Network on the side. You can close that. And what you're seeing, hopefully, is this cat dude here is the thing that we're going to move around inside the program. You're allowed to change it and bring a Powerpuff Girl or a ball or whatever you want moving around, and that's fine. I'm going to use the cat just because it's easier. Down here, it's a picture of the cat program. I'm allowed to have multiple different images. They're all called sprites. And I can make new ones. And so over here, you can see the different kinds of ways I can get it from a picture or from a file, or I can paint my own, or I can load it from their library. And so if I have multiple sprites all doing their own thing, that'll be listed down here. The giant blank space over here is the program. And what's cool about the program is it fits together like puzzle pieces. And so you drag over the piece, and the beginning, so events says when I start, and this says when the green flag is clicked. That's this green flag. And what I could do is say move 10 steps, and see how it kind of clicks on there. There's like a white line that says that they're going to snap together. And if you know they're together, if you can move the whole program together. Okay, so this is the world's simplest program. It says when the flag is clicked, move 10 steps. Now 10 steps really means 10 pixels worth of distance on the screen. So every time I click the flag, he's going to go 10 units across. Okay? And every time I click it, he moves. If I want to, I can drag him over here and restart him. And do-do. If I want to add another command to it, I could stick one right below. And so I can, now this says when the flag is clicked, move 10 steps and turn 15 degrees. So you can see him moving and turning across the screen. He really is moving. You just can't see it because the number of steps is so small. Let's change into what you can do is you can click in here and change this number. And now he's going to move 50 steps, boom, and turn. He's going to kind of go forward from whatever way he's facing. Come back on the screen, cat. So what a program is going to look like is a bunch of puzzle pieces linked together, and you go from top to bottom in order. So when the flag is clicked, first move 50 steps, then turn 15 degrees. And if I put, I think it's, where is the, you can make him talk. It looks, yeah. So you can say hello for 2 seconds. I can stick that in between. Okay, so now the program is, when the flag is clicked, move 50 steps, then say hello for 2 seconds, then turn 15 degrees. And if I click the green flag now, he will move, say hello, and then when he's done saying hello, he'll turn. You see how that worked? I'll do it one more time. He's going to move, then say hello, and then when he's done saying hello, he'll turn. Move, hello, turn. Okay, so the order in which the programs go, the order in which the steps of the program happen, so every individual puzzle piece here is a step of the program, and the steps of the program happen in order from top to bottom. Okay, and I think that what this next costume, let me get rid of this turn 15 degrees. Is there a way to point in direction 90? So that way whenever I start you point back that way. I think you can make him look like he's running. I think he has 2 costumes. And so you can click, and he's going to say hello for 2 seconds, then he's going to boop, and move his feet. So next costume changes him from one look to another. Hello for 2 seconds, and then change your feet. And so there's a lot of cool stuff you can do with this and play around with it. And so what the lab's going to do is walk you through the different kinds of things you can do with this program, and different sorts of stuff. What I want to show you is go back to what I was saying before about how high-level languages give you these abstractions. First of all, notice that at some point, every one of these instructions needs eventually to be turned into some kind of machine language so that the computer can actually do them. So one of the things that's happening behind the scenes is every one of these instructions, the point in the direction, the move 50 steps, the next costume, all that stuff, is getting interpreted as machine instructions, those zeros and ones, kind of like you did in the machine language part of the lab, in the homework, to do some, I don't know what it would be, as some combination of machine language steps, and those steps are getting executed, and what ends up happening is the cat moves around. Okay, I don't know. It's this is MIT people making this up, not me. I don't know exactly how that works. I just know that it has to work that way because the computer only understands machine language. So everything we're doing here is an abstraction of probably a lot of machine language instructions. Okay. Next thing is to realize, so I said we also have abstractions of things like do stuff forever, do stuff over and over, do stuff sometimes. So what we can do is they have this control button, and the control button gives you ways to control how he moves around or when he moves around or something like that. So what you can do, for example, is take this repeat box. And so what we can do now is, so you see how there's a hole in there inside the repeat box? It says repeat 10 and then an empty space. That empty space is the stuff I want to repeat 10 times. So what I could do is make him move 50 steps. I'm going to make him say hello for less than 2 seconds because that's a long time to wait. For half a second. And then next costume. Maybe I'll make him move 5 steps instead of 50. And so I'll start him here. And what's going to happen is he's going to say hello and move and change his costume 10 times. Okay? And if I repeat it 50 times, what's going to happen is I'm going to do all 3 of these steps repeated 50 times. And the reason it's doing that is because all 3 of these instructions are wrapped inside this repeat 50, and the repeat 50 kind of encompasses do this stuff, and internally it's keeping track of how many times it's gone and how many times it has left to go. And when it's done with all 50, it will eventually stop. I don't know how many times it's gone so far. I'm starting to worry the 50 is going to... There it goes. Okay. It reminds me of the cliff climber on The Price is Right. You know, the yodel guy. Yodely, ho, yodely. Where he goes up and up and up and you never know when he's going to stop. But that's because I'm old. So this repeat is an abstraction of all of that jumping and things like that we had to do an instruction a bunch of times in the machine language. So again, somewhere the instructions to do this over and over gets translated into machine language, and there exist jumps and registers and stuff like that happen over and over again, that happen in the machine language, that are happening. We don't know about them, and we don't care. So the benefit of having an abstraction is we're presented with something that looks like we're moving a cat around, and all of the details of, this is really done with machine language and binary numbers and registers and blah, 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 are not something we have to worry about and deal with. We deal with the abstract concept, not the details behind it. That's why abstractions are useful. Okay. So another one is we can try the if-then statement. Let's think of a good thing for the if-then statement. This is a good one. So how about we make it move 5 steps. So when the arrow is clicked, move 5 steps. You're not going to be able to see me do this. But let's do it this way. I'll make it an if else. So if you don't like your piece, you can drag it to the bottom. You can drag it away. I'm going to make it an if then else. And I'm going to ask if the space key is pressed. I'll make him say hello. And if an else, which means the space key is not pressed, I'm going to make him say, I don't know, what's the, say, yo, for 0.5 seconds. So now what's going to happen, the way to read this program is when the green arrow, the green flag is clicked, he's going to move 5 steps, and then he's going to see if I'm holding down the space bar. If I am holding down the space bar, he's going to say hello. If he's not holding down the space bar, he's going to say yo. You're not going to be able to see me holding down the space bar for obvious reasons, but right now I am holding down the space bar, and I'm going to click the green flag, and so he moves and says, hey, why didn't that work? Huh. Well, you know why? Because I suck. How about if mouse down? That's probably a better one. If I'm holding the mouse down, then he'll say hello. He'll say, The problem is I have the mouse down to click the flag, and so it thinks the mouse is still down. Let me think of a better answer. A better... Well, that's a good one. No, it's not. It's not a good one at all. That's a good one. If touching edge. All right. Now, let's try this again. He's gonna move 5 steps. If he ends up touching the edge, he's gonna say hello. If he's not touching the edge, he's gonna say yo. So this is one you can see. So I'm gonna click it. He's not touching the edge. He says yo. I'm gonna keep on moving him until he ends up touching the edge. Eventually, he's gonna run into this wall. So the way this works is if he's touching the edge, then he says hello. Else, which means he's not touching the edge, say yo. So all these yos are coming from him not touching the edge. Eventually, he's going to touch this edge. I guess the whiskers don't count. There it is. And now he's touching the edge, and he's saying hello because he's touching the edge. Off he goes. Okay? So, again, the if and the... You guys, I didn't tell you were doing this, but you guys wrote an if-else in your machine language homework when you were loading the 2 numbers from memory and seeing if they were the same. What you basically said was, if they were the same, then put a 1 in memory, else, which means what do you do if they're not the same? It's probably because of the clicking. Sorry about the voice stuff. If, I lost track of my train of thought. If the 2 numbers were equal, then put a 1 out in memory, else put a 0 out in memory. That's what you guys wrote, okay? The other thing you can do here is, we talked about the abstraction of variables. We can make a variable, I don't know, call it x. And what I can do is, let's do this. Repeat 50 times, move 5 steps, and then set my variable to, what I want to do is make this variable count how many times it's happened. So what I'm going to do is set x, my variable, to the old value of x, oh you stink, to the old value of x plus 1. And what that'll do is it'll increase x by 1 every time he makes a step. Get in there. And then when I can make him say, I'm pretty sure I can make him say x. Can I make him say x? Yeah. And so what he's going to do is he's going to say whatever number x is every time he makes a step. Okay? So 50 times, he's going to walk across the screen, move 5 steps forward, and say whatever is in this variable x. And what I've just done is made a program where this cat walks across the screen and counts to 50. And I did that by having a variable that kept track of the last number he counted, by adding 1 to it, and by saying whatever that number was as he went across the screen. So the lab, so if you're saying to yourself, boy, I have no idea how to do any of this, and he's going too fast and it's very complicated, that's fine, because the whole point of the lab is to walk you through how to do this and how to make them and how to make the program and what the different commands do and all of that stuff. What I'm trying to explain to you now is not learn every single command in Scratch. Even the lab, there's too many commands. What I want you to see is the sorts of stuff you can make it do and the sorts of ideas about how it works. The idea of the puzzle pieces, the idea of wrapping a bunch of stuff you want to do together inside of another instruction, the idea that pressing the green flag starts the program, the idea of what a variable is, the idea of what a repeat statement does, that sort of stuff. So up here is the title. I guess I'll call this CS 103 June 7 lecture. And the other thing is, once you have this account, you can give it a name and make sure that you, if you want to change it later on, you save a copy so that you don't lose the old stuff, because it's going to replace whatever you're working on every time you log in. And then make sure you share it by pressing the share button. And so what that does is it takes you out to your personal account on the Scratch server, and here the program is. And so when you hand this in, what I want you to do is share your program and send me the link to the program so that I can see it and run it and play with it and use it. Okay. In the lab, I show you my account, and my account has in it, well, now it has this program from lecture, but it also has a couple of other programs that I want you to play around with in the lab. This program is what you do is you click See Inside. This Cat with Arrows program lets you, when you click the flag, use the arrow keys to move the cat around. And I probably should fix this so that the numbers are correct, so that a down arrow moves you -10, whoops, and a left arrow moves you -10 in the X direction. And so the idea here is, when I click the arrow, the up, down, left, and right arrows, which you can't see me pressing, are moving the cat up, down, left, and right. Okay, and so that's what this project does. And the lab will show you how to do it, and the lab will show you how to modify it and stuff like that. The other program I have up there that I want you to do in the lab is this button move. It's the same idea, but the homework may want you to move the cat based on buttons. And so here's an example of a program with a bunch of different sprites with a bunch of different buttons to do different things. And when you run this, clicking the button makes him move in different directions. And so this is my example of showing you how to make the cat move based on button presses as opposed to arrow keys. Again, it'll make more sense in the lab. What I want to show you is the way you get. I'm going to give you a link in the lab, and what the link will show you is this program. Okay, and what you might want to do is save a copy of it to your account so that you can then edit it and do your own things to it. So, I wanted to show you all this stuff. I know a lot of it's going over your head. That's semi-intentional. that it's going over your head, because you're not meant to know from me just talking about it how this stuff works. The point of the lab is to make you play with it so you can figure out and work with it yourself and see how it all works. Okay. Um, but to get an idea for the kinds of stuff it does and the kinds of things it looks like and how running it ought to look. Okay. So that's what I wanted to do today, was show you this. Any questions on at least the idea of what's happening here and what you should kind of be doing in general? This all sort of makes sense? Okay. Um, Again, just like the webpage homework, you're gonna the lab is pretty long and the homework is kind of long. So give yourself time to do it. It would make my life easier if you guys could find some time between now and Thursday's class to go over this and at least play with a little bit of it, so that if you can't get it to work at all, then you can ask me for help. And if you're really stuck not understanding what's going on, I can spend time in Thursday's class working through it with everybody while I'm here talking to you. So as much as you can do in the lab between now and Thursday, and then come on Thursday with questions. When you run out of questions, I'm probably going to do some algorithm-y design stuff to get you ready for the last week. So it will be different. So kind of like last Thursday was not really web page stuff; it was slightly different. This Thursday will be not really Scratch stuff; it'll be slightly different. But I'm going to spend as much time as you need going over this and answering questions and helping you guys. So come with questions so I can help you. All right? Anything else? If not, I will stop and see you guys Thursday. See you guys.